Okay, so thank you. Thank you for the invitation and thank you for coming. So my intention is to tell you something about our project of formalization of combinatorics on words in Isabelle HOL, and thereby as a second goal of the talk, maybe the more important one is to give you some introduction into Isabelle HOL prover. So that's the goal, that's the aim. So I will start with my motivation. So my motivation was very concrete. I was working on a problem of classification of binary equality words, which is a large classification problem in word equations, let's say. You can think of it maybe as a much less prominent counterpart of similar classification things like classification of simple groups, which also was formalized. So the motivation is similar here. That at some moment it became clear that the further advancement of the project is not so much. Is it okay? Yeah, it's not so much. Doesn't so much require some new ideas or. Yes.
So the classification of the binary equality of work is a kind of group theory, right? You say that what is it?
I will say something about it in a minute, even if it is not the main focus. That's now I am mentioning it as a motivation. So it was clear that in order to organize and to be able to be sure that, for example, the big case analyses are complete, that it is kind of beyond the human capacity, and so I started to think about using some kind of prover, and eventually we started this project of formalization of combinatorics on words, and it was boosted by this Gacha project which we had. So when I'm saying we, I mean mainly Štěpán Starosta, who is my main co-author and collaborator from Czech Technical University. But at the Gacha project, we had also some students, in particular Martin Raška did some tremendous work. Probably the best part of our code is written by Martin Raška. And the results can be publicly.
Ano, yes, 1, 2, 3. 1, 2, 3. Okay, so the archive of formal proofs, which is a place where all these formalizations are collected. That's official Isabelle's repository. And we have there a couple of theories, those most, let's say, mature. And then there are these, I think these are the information that I can easily say, even if nobody hears them, so I can continue. So the GitLab repository. The GitLab repository is also public, but we don't update it. Is it?
Sorry, apologies for the introduction. So okay.
Is it? Yeah. Okay. So I'm just saying where you can find our project. That's probably easy to find out anyway. If you didn't hear me. So this is how the AFP archive of formal proofs AFP looks like. So I search for my name, and there are a couple of theories there, and this is the GitLab project where you can clone it. Of course, you can see that it's 1 year old, so we don't update it very often. So the live development is on a private repository. But if anybody is interested in joining, then of course we will be happy to make even this developing repository available. Okay, so but let's now turn to the provers. So of course, as everybody knows, the provers are kind of making through the old dream of having rigorously formalized, rigorously checked mathematics, as probably started by Gottlob Frege. This is a picture you should certainly know from the from his Begriffsschrift. But so on one hand, the modern provers are fulfilling this dream. On the other hand, they are kind of changing it or departing from it because Frege had in mind the first order logic, and this does not seem to be a very good idea for formal proving. So this is the quotation from Larry Paulson, which is actually the creator of Isabelle, that maybe the dominance of first order logic in mathematics is being challenged, even if it is probably not completely true in the mainstream mathematics yet. Okay, so now the question is like, why Isabelle, right? So there are, okay, I should comment, there's Isabelle, there is Coq, which by this year they should be renamed to Rock. They promised it to do it by the end of the year. I don't know whether they do it. Then the lean is probably the most progressive nowadays, and we shouldn't forget about our Polish colleagues and Mizar, which is still quite remarkable achievement, even compared to today's system. Let's say more recent systems. Okay, so now the question is why Isabelle out of these? Yes. So well, of course the difficulty is that you don't have a comparison when you start. So you have to make a choice, which you may regret. But I must say that I don't regret my choice of Isabelle. So I will tell you why. So first, there is probably a superficial reason, is that if you look at this quite famous web page of 100 theorems, so you can see that Isabelle is safely leading the field. There are 90 theorems proved. Cog has 79, Lean has 76, and Mizar 69. So in this sense, still Isabelle is like the largest system in this sense. But from the user's point of view, like the two main reasons why I'm happy with the choice of the system are the first two. And the first one is that the Isabelle contains a layer of structured language, which is called ISAR, which its intention, and I would argue quite a successful one, is to make the code as close to the normal mathematical language as possible. So this is something which I think is a great added value. And the second, or maybe even the first advantage of Isabelle, which is a source of envy from other systems, is the existence of Sledgehammer, which is integration of the prover with external automatic provers. So here I should stress a common misunderstanding, which probably you are not victims of that, but I should stress that we should distinguish between proof assistant, which is just checking your proof. You have a proof, and it is just actually making it more difficult, even because it's always asking the questions like, what did you think? And automatic prover, right? Automatic prover, everybody dreams about automatic provers in a sense that they will prove theorems for you, right? So Isabelle and everything we are talking about here are proof assistants. So you already have your proof, and you just want to formalize it and to verify that it's correct. But still, there is some kind of automation. And Sledgehammer is really very, very extremely well working integration of Isabelle to external provers, including set solvers, satisfiability modulo theories, provers, and other things, which you don't need to understand, and I don't understand them very well, but they are at your disposal. I will show you this in the practical part, which I think roughly half of my talk will be a practical demonstration if everything goes well. And then there are other reasons which are less, let's say, user point of view important, but still that Isabelle is generic prover. I think it's a unique one. Certainly it's a unique one out of the list, which means that it can encode different object logics, right? So there is a layer of meta logic, which is like caring for different object logics. So there are different libraries in Isabelle for different logics. There is quite big ZFC library, which will like makes it a competition for Mizar, which is a set theoretical prover, but it is just set theoretical prover, right? Mizar. Or you can have first order logic, right? You can go back to Frege if you want, but most developed, and it's kind of a pedigree object logic for Isabelle is HOL, right? I will tell you something later about it. So when I am saying Isabelle, I mean Isabelle HOL, actually. This is also, people usually say just Isabelle, but you should actually say Isabelle HOL. But I will tell you something about it later. Everything is coming. So, and the fourth feature is that it has a polymorphic simple types. So what does it mean? Well, polymorphic means that you have terms like A list, where this A with the apostrophe means type variable. So you can reason about lists over all types at the same time, right? So this is a polymorphism. But it's a simple type, so this is formulated in a negative way. You have nothing like n-tuples in a sense where n is a parameter. You have pairs, you have triples, you have quadruples as a type, but you don't have a parameterized type, right? So actually this feature it's not at all clear why I should list it as an advantage. On the contrary, many people say, okay, thank you for your talk. We are not interested, right? If you cannot encode n-tuples, like what do you want to do, right? Okay. So that's the real question. Right?
In the different versions of type theory, independent types, you have n-tuples and so on. But in Isabelle's version of type theory, you don't have it, but you have this polymorphic.
That's what okay. So I was not sufficiently clear. So the fact that Isabelle is a simple type is, of course, distinguishes it maybe in a negative way to other systems which are dependent types, where such things like n-tuples are encoded, right? And it seems like an obvious advantage. So I'm going to comment on this, right? Because it's a big question, like whether simple types are actually not obsolete, right? And I will illustrate it on a clash between the two big people, between Kevin Bazard and Larry Paulson. So probably you don't see that that's the title of the frame, which is the Grothendieck sheaves or Grothendieck schemes challenge, which was posed by Kevin Bazard in 2020, and characteristically, it was not just a challenge to lean people, but Bazard somehow felt obliged to attack Isabelle, right? So he was saying, like, what? It's from the blog, right? So blog, okay, it's a bit informal, but still, it's a public place. What can Isabelle HOL actually do before it breaks? Nobody knows. Can your system even do schemes, meaning Grothendieck schemes? I don't know. Does anybody know? If it cannot, then this would be very valuable to know, because it will help mathematician early adopters to make an informed decision about which systems to use. So it's not an insidious comment, right? It's not neutral. It's a hardest competition. You may ask whether it's related to the fact that Isabelle was created in Microsoft. That this competition-oriented spirit is somehow built in. But anyway, and then he continues, I am not sure that it is even possible to write this code in Isabelle HOL in such a way that it will run in a finite time. And now the types come into play, right? And a sheaf, which is another algebraic point, ring sheaves, that's another algebraic notion, is a dependent type. And your clever HOL workarounds will not let you use type classes, right? So this is really something of a challenge. And so does anybody know? Well, nowadays we know, because Larry did what he was supposed to do as a father of Isabelle. He just implemented Grothendieck schemes in 1 year, right? Or the publications in 1 year. And he, of course, didn't miss the opportunity for a subtle, ironic answer, saying, okay, challenge is accepted and met. And then he quotes Kevin Buzzard's blog. Kevin Buzzard reported on his blog the difficulties he faced during his formalization lean. Now, quotation from Kevin's blog: the project is completely incompatible with modern lean and MATLAB. During our proof, we ran into huge problems and things like that, which is, why did he say that? I think this was like to create the impression that this is really a huge thing, there are a lot that's very difficult, And now Larry dryly says, okay, we had no such problems in Isabelle.
So that Isabelle HOL better than Lily.
In this case, well, you can say what's better, but at least the question, the suggestion that the simple types cannot deal with this advanced algebraic concepts simply was shown to be wrong, right? You can do at least this, that's kind of philosophical question, whether everything that can be done in dependent types can be done in simple types. It should be better formulated, but so far, sociologically, this has been done, right? And you can read the paper. There is, of course, much more about it. And then again, types can come back, right? It seems that this difficulty cannot possibly have a direct counterpart in Isabelle, since it arose from the difference between the so-called equality types and the definitional equality, a difference which is peculiar to dependent type theories. So the point is that you have a trade-off, right? Dependent types are certainly more expressive on the surface, at least. You have to do things differently in simple type, maybe in a more complicated way. On the other hand, they are simpler, right? So they're more transparent. Also, Larry is asking, I don't know whether this is still valid, but he's saying, okay, maybe simple type theory will be more available for the AI, to find the solutions in automatic creation of proofs. Maybe in simple type theory may be easier than in dependent types and things like that. Okay, so far for politics, right? So far for propaganda, and now back to real things. So now this is just a very short history of Isabelle. Yes.
Are they things you already have to make when you're formalizing theorems, or is it when you start doing proofs?
Sorry, I don't hear very well. So
when you have that theorem and you just want to state it in this language,
yes,
you already need to make decisions about types when you state it.
yes, modulo polymorphism. So that you can say that it's arbitrary type. You can use type variable, but you have to state type.
So in different systems, you'll get different theorems.
Different theorems. So
Lean or whatever.
Yeah.
You'll get a different translation. The theorem will be different.
Well, if it depends on type, then yes. I mean, if you have a theorem about natural numbers, then your type will be natural numbers. But if you want to, for example, I mean, speak about n-tuples, so certainly in Lean you could express it differently than in Isabelle. But like speaking about n-tuples, it's easy, right? You can take a list. You can represent n-tuple as a subset of lists, right? So then it will be a pair. Right, it'll be a number, length, and the list. Right, you know, there are like this kind of workarounds may seem naive, but what I presented before just shows that these naive workarounds work at least for Grothendieck schemes, right? Okay, so is it kind of answer? Yeah. So the history, like everything starts with lambda calculus, first untyped, then typed, right? And then maybe less known is really an important point is landmark is the Dana Scott's technical paper on interpretation of lambda calculus in terms of continuous function. This created what is called Scott domains. And it was written in '69 and published only in '93. Also lovely reading introductions and this like historical reflection because it was okay. There's also the story why it was not published is also interesting. And then it immediately or soon after Scott made this theoretical work, it was implemented first by David Milner and then many other people, but I'm mentioning Paulson. But many other people contributed to the implementation of Scott's interpretation, and this became known as logic of computable function, LCF. Sometimes LCF is conflated with PP lambda. So PP lambda is the logic, and LCF is implementation of PPL lambda. So it's almost the same thing. And so this LCF has a long history, many versions. And another important point is that Milner, for sake of implementation of LCF, created a meta language, which is a programming language of its own now, but it was created for this goal, for implementation of LCF of Edinburgh version in 1973, right? And then Mike Gordon made another step when he created the HOL. Right, so HOL stands for higher order logic. So higher order logic is a general term, but in this specific case, HOL is a particular logical system. I am not going to say anything about what's the difference between LCF and HOL, but it's like another development step. And then finally, in 80s, during 80s, Paulson created the Isabelle, and Isabelle had this revolutionary change that it really was not logic oriented. It has this general, it is a generic framework for arbitrary logic, right? So if we speak about Isabelle HOL, this is not that important, but what is important, and that was one of my points why I like Isabelle, is that these two layers, the object logic and the meta logic, is kept, right? Which I find very, from the user point of view, very nice. And even like pedagogically, you see what's going on. Like, of course, you understand that even the meta logic could be somehow incorporated into object logic, and you got all these like paradoxes possibly and or not, and so on. So it's also interesting, but keeping it net distinct has some advantages. It has also some disadvantages, of course. Maybe we will see it, hopefully.
Somebody who's not so familiar with these terms, meta logic and object logic.
Okay.
How are they reflected in like?
I think I will postpone this to do the demonstration. Yeah. But also this is I continue. Maybe this is a summary of what I have just said. So when you get when you open Isabelle, you first open the user interface, which actually this is kind of accidental feature, but very strong feature of Isabelle is that it comes in a package. everything is integrated, right? Not like, for example, in case of Lean, that you have VS Code and then a plugin in it. You have to have actually, Isabelle is also a plugin to Jedit, but you have to have it, you cannot install Isabelle on your Jedit. You have to take it as it is, right? So this is what you open, that's editor, you will see it. And then there is this ISAR level, which, for example, contains the word assumes, right? Gives you a flavor of what does it mean, like to bring it closer to human language. Then there is Isabelle, HOL, right? So maybe I should just say HOL. It's this object logic. And there is this meta logic, which is called pure. This is this PP lambda mainly, but it is not exactly that. It's called pure in Isabelle. And then everything is implemented in standard ML. And this is actually not just weird information, because this ML, as I told you, is also a logic-oriented language. So actually you can write even directly in ML. Some people say that this is crazy, right? Because you can have this ISAR, nice proof, and then you can have ML code, right? Which is completely non-readable. I will show you all this, right? So this is just an overview. Now I would like to tell you something, just one slide about this project of mine, because this is really not that important. It will be completely different talk, but let me just tell you what we are trying to achieve. So what's the binary equality word? Unfortunately, that's in the title, not seen. So a binary equality word is defined as a word over a binary alphabet for which there are non-periodic morphisms such that which agree distinct to distinct, of course, that agree on that word. Okay, example. So for example, AABBBAA is not a binary equality word. Remarkable fact is that this was a paper. It's a word of length, right? What is it, 7? No, it was a paper that this is not a binary equality word. Maybe, maybe not in the best journal, but still it gives you an idea that it's not an easy task, right? And what it means, if you don't like follow the language of morphisms, it means that if you have this equality on words, so we have 4 words, X, Y, U, and V, and you want them to satisfy this equality, it means that this is impossible, except for trivial cases like all 4 words can be empty, or all 4 can be the same, or most generally, they all have to be power of the same word. Right.
So even see that on left hand side.
Okay, and what's this? And what's this? Yeah. Okay. Oh.
X, there are 6.
Oh, X, Y, Y.
And then 7. And the other.
Oh, missing V. Sorry.
Yeah. So,
missing V. Sorry. So this is GW.
Yeah.
AABBBAA is W. This is GW, this is HW, right?
Yeah.
So GH, for example, GA is X. And
Yeah,
okay,
yeah.
sorry, very sorry. I'm very sorry.
Missing.
Very sorry. Yeah. Missing V. And this is the situation. Okay, I think you don't see the white. You probably can't see the difference between gray and white. Okay, over there, yes. Okay, so the white part is the one which is not yet classified. Right. Roughly, which is in terms of the number of A's and B's, right? The coordinates are the numbers of A's and B's, where B is the longest of the 4 words and something like that. Okay, that's it. That's end of my slides, which is very good. So we have now half of talk really for the Isabelle itself. Okay, so this is Jedit. This is Jedit with a lot of features, right? So this so I have a theory which is called presentation. I import a lot of things. I start with main, which is just a normal starting point for basic things you would expect, and then I have a lot of other stuff, right? For sake of I don't know whether I will need them all, but it doesn't matter. Okay, so first thing, I want to explain like what this difference between logic and metalogic is. Right? So first I open a notepad, which just means that I am just writing things out of context, right? So it's like a playground. And I write fix AB, like everybody understands, right? What fix AB means. Like I pick two ABs. I don't specify types, by the way. I don't specify types. If I hover over it, I can see that, you know, the type is somehow unspecified. I even don't know what this underscore means, but type is not yet specified. And then I assume A and the implication, right? The most simple thing. And now when I look at here at what B is, I see that B is bool, right? Suddenly. Why? Well, because Isabelle made so-called type inference. It understood that in order to make it sense as an implication, it must be bool, right? So now without, I could write here bool, right, as well, but I don't have to. Okay, that's a wrong syntax. I could do this still. Sorry, you can see that the type inference is very common, so I don't even know what's the proper syntax. Fine.
What if you wrote A implies A?
I could do the same, yes. So it's still bool, but B is not. Okay, B if I term. Okay, here I can see what you know, there is in the output window. I can see this is like check, right? So the A is bool. I didn't have to hover. A is bool. What's B? Well, okay. B is some type. Not known what, right? But here already, right after here, the B will be already bool. Oh, not. Okay, because this is just term. I didn't declare anything. That's just, I'm checking what the term is. I don't say, I don't assume it. So, okay. So the A is a bool and it is object logic type, right? It's object logic type. Is HOL type bool, right? So it is defined in object logic. Pure metalogic has no true or false. It has no bool, right? It's a very simple. I probably have no time to explain you like what the pure actually is as a logic, but that would be another talk. But when I look at this claim, it is prop, this time prop, right? So this is the main difference, right? Prop is a type of pure. Actually, that's the only type, right? Plus the combination of functional combination, right? More or less. So prop is the basic type of pure, and that's not bool, right? So I am saying this implication is a pure implication, you know? So it says it is the meta claim, like in English, it's a formalized English, the higher level, saying A implies B, meaning when you can prove B from A, right? It's not A implies B in a sense of a logical connective, right? That's a different thing. I will come to it. Okay, and now I want to prove B, right? Typical just a modus ponens, right? The mother of all proofs. What went wrong here? Okay, I need A to B. Okay. So I now can prove B, right? Using implication imp, right? That's, I gave a name here to imp, and A. So using these two things, I can have B. And now, okay, now the goal, if you look at before, the goal is chain facts. That's called chain facts. So this is like, okay, I said I will not, but this is like what you know from logic, like A, B, like A implies B, B, right? So this is like the chain facts, right? That's, we have these two facts, right? Somewhere stored. right?
This is the application window. The top half is the textual editing, but some of the orange things is annotations the program has added.
Okay, these annotations, I wrote them for you in order to see what's in the output window. Even at the bottom of the screen is just a part of the plugin, right? So that's a window, which tells me the current state of the implementation, right?
At line 16.
At line 16, yeah, at line 16. Yeah, okay, that's the state at where the cursor is, right? So if I go one line up, I have B, right? So here just I have a goal B, right? Now I go down and I say, okay, now I have the same goal, but I have two facts at my disposition.
But it's proof because you use the word have. That's why it's talking about proof.
Have means an auxiliary claim, right? You will see that's why I am in the notepad, right? So it's like a not proper, it's just a fragment of a proof. If I cancel the notepad, Isabelle will tell me, I don't understand what I'm trying to prove, right? So you will see that on line 19, I will already go into the proper mode. I will state a lemma, right? So this is just really playground, right? Trying to, so have is an auxiliary claim. So this is something like a lemma, but auxiliary, like, okay. And of course, how do I prove it? Now the most important thing is how do I prove it? Well, I had a dot here, so that's just the most simple thing. Now, of course, now the interests of a user and of a logician will part ways, right? Because logician wants to know what happened. User is happy that the proof was accepted. Right? So I don't know which one. I will try to go both, right? But something, what I could do here now. Okay, suppose that I'm a complete beginner and I don't know what to do, right? So I can write try 0, and I will get a bunch of methods or tacticals that are able to prove it from these assumptions. And here I stop caring. I don't know how Otto, Blas, Sim, Argo, Pressburger, or Linarit, or Fast are doing this. All of them can do it, and I don't care how, right? So I could write anything here. Instead, I could write by Blas, for example. Right? But I can also write dot, which is kind of like the most obvious proof. That's a method which even doesn't have a name, right? So again, what these tacticals do, well, they use some internal tricks for proving, which also we could discuss what these internal proofs tricks are. They are mostly backwards chaining, like saying that okay, maybe it will become clearer in further examples. So here, I have proved B from the A implies B and A, right? Okay, is it roughly? Okay, so now something more serious.
You go as far as to say that int, as you defined it, is a function.
It is. Oh, I wanted to show this. Okay, actually, if I want to say how it worked, actually, this was my intention. Thank you very much. Yeah, I can since okay. One of the main exactly one. I can even open the proof. If I don't, I cannot. Can I not open proof in Notepad? Oh, probably not. Sorry. Okay, so I will show you later. But okay, using imp, and now okay. That's strange. Okay, that doesn't matter. I could write this of A, and it gives me B, right? So exactly, right? The implication is understood as a function, but the meta function, that's the difference, right? It's a meta function, and that's the implementation, right? So you have in pure, you have some rule for implication, which is axiom, and this is in ML implemented by a function which accepts B and A and returns B. So that's another level which we cannot see, this implementation level, but this implementation level remained in the notation of capital Of. Right? Capital Of means application into the, it means satisfying one of the assumptions. Okay, okay. Where's the proof? Yeah, good. Yeah. Good. Yes. Yes, good. Long answer to short question. It can be arbitrarily long probably, but depends on what you mean. Okay. Now, no, I want. Yeah, I understand. So LCF, logic of computable function, one of its main features was that one of the design features of LCF as a, let's say, software project, not mathematical project, is that it does not store proofs. It executes them, right? So if you want to see a proof, let's postpone that. First, let me first answer the question which you didn't ask. If you want to be sure that the proof is correct, then you have to look at this ML code, which you will see what it really did, and it accepted it. Right, so you can, it's fairly, this is sometimes called small kernel approach, that you can verify the program in ML, and you will know that the program ran through sound applications at it output B, right? Okay, but if you really want, and so the first answer is we don't care about proofs. That's our design decision. So you can say, okay, so we are not mathematicians and so on. But then the proof as such is called proof object, and proof object is a record of what happened within the computation, right? And you want to show it. Okay, now my question would be, now if I try to defend the decision not to store object proofs, I would proof terms, that's called proof term, not store proof terms. First, you couldn't, and probably still cannot store them because they are too big. But my question would be, what do you want to do with it? And you probably want to verify it. How will you verify it if it has 1 gigabyte? Well, you probably take a program and run it through it. That's exactly what happened, right? But if you really want to see it, then you can do it. I can show you some incomprehensible text file which will contain proof, and I never did it. Okay, I did it. I saw some proofs. I never tried to understand the language in which it is written, but you can see some text file which is a proof. The proof object can be generated. You have to do something. You really have to say, yes, I really want to see the proof object, because then you immediately consumes all your memory if you switch on proof terms. But you can do that. Is it?
Some statements which I want to do, so I use this, and then it tells me
Yes.
But
yes.
making a proof assistant is something that will help me to write a paper.
Yes. Actually check that if I make some mistake like
just the information, and yes, it can be proved.
Yes.
Then,
well, but okay, so well, I would say that's why I started with this example. My question is, do you really claim that applying A to the implication A implies B gives you B is not a sufficient information for you as a mathematician? For me, it is, right? So the remaining question is, how is it implemented? And that's what I'm not interested in as a mathematician, right? You are right that further below, we will see, or maybe not today, I can give you an example where you will not see how the proof went through. And then it is on your decision as a designer, right? Either I trust it and I go on because I have something, I don't know, I have a deadline and I need my final program to be formalized and I don't care that I don't understand the, okay, and things like that. Or you say, I don't understand this step. And that's what I'm doing like every day, or let's say when I'm formalizing, right? Sledgehammer, I will show sledgehammer. Sledgehammer already now gives me proofs that I don't understand, proof steps. And then I am urging my collaborators, and I certainly do it myself, that I am analyzing it and break it into steps so that I consider every step obvious. And I think that's probably what I am just going to show you in this example, which is an example which is already, that's not a toy example anymore. That's a serious, well, the basic, of course, basic course on combinatorics of words theorem, but it characterizes all solutions of the equation xz equals zy, right? So now you can make your opinion whether it's still readable, right? So assuming equality, and that's a name, EQ is a name, equality xz equals zy, and assuming that x is not empty, then obtains, it is like there exists, but let's say, then I can find uv and k such that x is uv and y is vu, so they are conjugate. And z is of this form, uv to the power k times u. This power, it's like power in word power, right? We have this fun, we invented this fancy, because the normal power is already taken from, okay. It's a free, it's for words, for lists. Yeah, that's another question, like what the words are. So they are free monoids, of course, but in Isabelle, they are lists, like data type lists. Yeah, in words. Okay, so now proof, right? So first have, okay, now I open proof. So what happens here? So I have a goal, right? And the goal is actually ugly. I don't want you to look at the goal because this is not a nice. This is not readable mathematically, but that shows you actually the difference between pure and Isar. Like Isar tells something reasonable. Logically, on a pure level, it is this, right? You may have an idea why it is this, but I don't want to spend time on it. Another important, interesting thing is that automation, right? This is software informs me that actually this is already proved. Not surprised because I have downloaded a lot of my stuff, right? So I am reproving it to show you the proof, but it already exists. Very useful, right? Very useful. Automatically it shows me, okay, so, sorry, this exists already. Okay, and then, but
This bottom half of the screen, is that the output from this, the proof in the top half, or just from the demo in the top half?
Here ends the one window, and here starts the output. No, that's not the whole thing.
I'm just wondering, is this significant way to put the cursor, or is it processing the proof that you wrote, or is this just?
No. It's where the it tells me that I have correctly stated a lemma. It understands the lemma, and it understands that it's my goal. So it tells me your goal now is to prove this. What it sees is that's exactly what I wanted to skip, because this is what obtains means. That would lead me to the what existence means in logic in pure. Right? Yeah, this is a pure logic formulation of there exists UVK.
Just I think to clarify, yes, where the cursor is important.
The cursor defines what the output window tells. Yeah. Okay. So now that's why I'm moving the cursor. So I go to proof. Okay. Nothing changed actually. Just the information that it is already proved disappeared. But you know, I could cancel this minus, which is, I don't know whether this is a good design decision, but if I write just proof, I let Isabelle guessing the way of proving it, right? This is certainly a bad idea, right? It tells me that I can prove the 4 things, So, it tells me, okay, you could prove it by showing that there exists UV such that this is true and there exists such that this is, and this is not how I am going to prove it. So I say, okay, thank you for such a suggestion. I'm not going to prove it here. But what's important here is that, there is some rule inside which was picked by the system saying, okay, I can see that this could be used by this rule. And the rule means that instead of this goal, you can prove these 4 goals. This is backward chaining, right? So you have forward proof is that you start from assumptions and go forward and with the goal. The provers in general work rather backwards, that you start from the proof and say, okay, how could I prove this? Well, you could prove it by proving these 2 things. And how to prove this thing? Well, and so on, backwards until you arrive to assumptions. Okay, but I don't like this suggestion, so I am going to prove on my own. Thank you very much. I don't accept your suggestion. Okay, so first, and now I can claim auxiliary claims, right? By have, right? I'm inside proof, so I cannot write lemma, but I can write have. That's what we saw in the notepad. So first observation is that z is a prefix of xz. Well, xz is zy, right? So z is prefix of xz. Obvious. I would tell to my student, obviously true. And that's what Isabelle says, using equality. Obvious. Double dots in this case, right? It's something slightly different from 1 dot, but that doesn't matter. Another method. From this, and the fact that x is not empty, it's actually a proper prefix, not only prefix, it's proper prefix. Okay, and therefore, and this is a big step already. And of course, the fact that this is accepted as obvious is based on what's on the background. But again, to my student, I would say, okay, if you have z and you have xz, well, that means that the x is repeated here several times and then possibly not. That's just an auxiliary lemma, of course. Like the system wouldn't know it without. No, I already have it somewhere. And I even said, when I proved this fact, I even said, consider it as obvious starting from now, which is done by putting it into the intro library, right? So this Isabelle considers as obvious because I told her to consider it obvious, right? So this is a part of your answer to your question. Like I could declare anything as obvious, right? And then of course it is what you said, that it stops to be informative. But again, this is assistant. It does what I want to do, right? I want to be sure that my proof is correct, and I am writing it so that I am happy with that. Right? I can write it. There are many like very ugly formalizations, to be honest, right? Very ugly. Right? Even in AFP, right? The referring process is very not as thorough as in lean case. Okay, and so on. Maybe I would say and so on, right? You go on and then you prove it, right? You can see that in these proofs are all only double dots, nothing serious, but you can see that it's. I told you that it doesn't mean much because I could cheat, right? I could. You don't know whether behind the double dot is some difficult lemma, but I would think that if you go through it, you will agree. We don't have time to let you to do it, but you would agree that this is really a textbook, like first year textbook proof of quite non-trivial fact, which kind of characterizes all solutions of this equation.
So just curious, you use one of these automated dot or double dot. How much time do you expect it
to be executed? Oh, very good. You are. I can tell you. 1 millisecond.
But I mean, this is typical, or like sometimes it could be like.
Let's see. I will show you. Okay. So now suppose that I don't like the octane, and I want to formulate the same thing as an existential claim. Again.
What's the meaning modifiers? Also.
Say again.
So in the previous scope, you have this couple of lines with additional modifiers, like also have or finally have.
Yeah.
So what is the meaning of this?
Okay, that's the ISAR. That's ISAR, and I should explain it like one by one, right? So have means like claim, and then unfolding, for example, or what? Which okay, unfolding means substitute. So unfolding, for example, here x is this x, so this is x. This x is uv equals x. So unfolding x means that uv's are substituted with x. This unfolding just means like simplify from left to right using this rule, right? And you can see that actually when you substitute x's here and then substitute this fact, which is also here, then you really get the if you unfold it, you really get z equals z, right? Just you can verify it. Just it should be seen, obvious, right? That if you substitute, then you get z equals z, and that's I admit I submit that as z equals z does not need further proof, right? So
lines 32 and 34.
okay, also have okay, I see. Okay, it means like that I have like a equals b equals c equals d in the paper. You have to break it in a equals b and also equals c and also equals d. I know. So that's an example already, or quite. This is a bit advanced example of ISAR, but you know these are the ISAR ways of saying you know that right. Okay, so this is like z y equals this and finally okay, finally this means like finally means that I am now using the beginning and the end of the chain. So now I am using from a equals d. Finally means from a equals d get okay. Okay. Probably I picked. I wanted to pick an example which is not completely like trivial, but yeah. Okay. So now suppose that that's probably the last thing I can do. I of course have another 1 hour of examples, but suppose that I don't like this obtain thing, and I want to state it in the object logic, right? So exists is a quantifier in HOL. It's object logic. There is no exists in pure, right? No such fancy thing in you know existence. What's that, right? By the way, so every logic has to decide what existence means, right? So, but I want in HOL to write down this, and you can see that the system does not inform me that it's already proved. It's not, because what I have proved before is not the same thing. It's very close, but it's not like this auto solve. It is just when it's exactly the same thing. Okay, so what can I do now, right? Again, as a beginner, as a complete beginner, I feel, okay, that's the same thing as conjugation prime, I call it conjugation. It's the same thing. It's just written in a object logic. I don't want to spend much time on it, right? What do you do? And now comes the glory of sledgehammer, right? So if I don't know, I ask sledgehammer. Which means that I am using these external provers, and sledgehammer does a highly non-trivial thing, translates the claim to the language of each external prover, pass it to them, and then accepts proofs and tries to reconstruct them back to the Isabelle language.
So not using the previous proof.
Using everything, using anything that is available actually,
Including the
even the imported things, even everything. You can you can slightly modify what is used, but generally everything is used. So everything, really everything. And what it did told me, okay, the Meson tactic can prove this using the conjugation. So it actually found out that the previous claim is useful, even if it were, somewhere. And as assumptions 2 and equality. Equality is actually assumption 1. So what I can do is, okay, and what I do is just this, right? And that's it. And again, am I happy with this or not? But if I'm lazy, I am happy. If I'm lazy student, I am happy, but I am not happy, right? So what I will first want to see what's going on. Okay, here there are several tabs, so I switched to sledgehammer. Now I go back to output. So now it is proved. By the way, okay, one comment. This is the final proof. So you can see that all these assumes is actually represented as implications, curried implications, right? So assumptions are okay, and also these question marks. Question marks means that these are so-called schematic variables. So this is another feature like that on the pure level. You have schematic variables, meaning like you can substitute anything in it. You would say that's a free variable. Okay, free variable is some logical concept, which maybe we don't have on the level of pure. So this is just schematic variable, meaning that it is a schematic claim. It's infinitely many claims. For any substitution, it's a claim, right? Which actually reveals another feature that what I will have to do to prove to use such a schematic claim is to make something that is called higher order unification, right? In order to see that something that I want to prove is actually an instance of this, it needs one of the most important parts of the machinery, which is some efficient implementation of higher order unification, which is one of the design decisions of Larry Paulson in '80s, and he probably spent several years into tuning it, and that was like the glory of Isabelle was that he was able to make higher order unification to work. Okay, but what I do, I have to stop. I can stop anytime. Yeah. No, I mean I can stop. I can stop now. But I think I would finish this. Probably I will finish this late 3 minutes maybe. So I will just tell you what I would do with this if I were like, what for me is a good proof. Okay. So what I did is that I have a macro because what was the, I had this form. That's a different form. In brackets, not very readable. So I have a macro which makes this. Okay, does it? Okay, which unpacks it. The same thing. I want to see assumptions. So I have these 2 assumptions. I have these 3 assumptions, and I have a goal, which is not visible here. Right. So on this level, so first recall that I have found this by sledgehammer. Now I am modifying it to my satisfaction. So I first opened it to see because before it said that Besson can prove it with these 3 claims. So I want to see the claims, okay? So now I see them. So the Besson is able to prove this from this. Okay, how? How? I can think about how. Well, first, I don't like the 2 assumptions. Okay, so actually that's just assumptions. So this is syntactic simplification. The 2 assumptions. I had a name for one, so it said equal plus the second assumption. This is better. Okay, but nothing changed here. So what can I do? Well, I see that of course this unifies with this, and this unifies with this. Okay, I can use capital O. Good, right? I have satisfied the 2 assumptions using this higher order unification, right? So going back once more, right? The clever thing that happened, which is not that clever in this case, it realized that this is an instance of this. When you unify X with question mark X. Okay. And now I think I would be happy now. I would be probably, what happened? Okay, first, I even don't know this because that's, but what happened? Did it work before? Okay, Mason is not able. Oh, interesting, interesting. Suddenly, Mason is not the right tactic to do the last step, right? Okay, so Mason was just a stepping stone for me. And now I try 3-0. Okay, Mattis is the right one. And by Mattis, the question was about times, right? So Mattis, this was 31 milliseconds. I usually for myself, I want everything to be under under 100 milliseconds. If it is over, I either work on it or mark it as further work needed. Pardon?
To get a faster computer.
Said under 100 seconds or 100 milliseconds?
100 milliseconds each step, each buy. If a buy is more than 100 milliseconds, then I think it needs some more attention. Unless, of course, this will change with the speed of computers, but so far, unless there are special cases, where you really need an. So I would be happy with this already. Right. The question is, how do we know that this is true? Well, this is something I told you I don't want to explain, but let's say that it has something to do with the introduction rule of existence. Right, so I can now you can try to guess, and that will be already quite difficult. What's the P, right? P is a higher order predicate. It's a predicate, maybe even higher order. It may be any predicate. So something like that. And of course, what was certainly also was the conjunction introduction, which is more readable. Right? Right. So Mattis obviously did a lot of applications, some chain of applications of these two rules. Right. It transformed the obtain to existence, and it created it joined it packed the chained facts into conjunctions, and that's it.
So these are axioms of HOL.
This is proved. I think maybe the second one. I don't know. I don't know whether they are axioms. I don't think so. But let's see. Okay, now it's lemma. It's lemma. Okay. We could trace it back. Like, what are the axioms? But again, this is already not a prover point of view. So I never really tried to have a complete list of axioms. Okay, thank you very much.
I wanted to ask you, because if you work on the limb, so what is the difference?
So the expressiveness of the language is definitely different, as Štěpán pointed out at the very beginning.
Yeah.
You don't have to use some tricks to express an idea like M-tuple. Okay, but it seems that these automation tools are somehow more effective in Isabelle, maybe because of this simplification. In respect to the.
And I would even say that the resulting text is less readable in Lean.
I think it's a degree of how familiar you are with the text.
Okay.
The syntax, because I find that less readable, but because
Okay.
I have much less time reading Isabelle code than.
Okay.
But I just wanted to point out that you just mentioned the higher order unification. I mean, it's kind of a technical thing, I don't know.
It's a logic.
Zero, but really,
That's for
Yeah,
the-
But at the practical level, so I don't know how powerful it is in this case.
So lean system also in the first order.
So, part of the interface with Lean is, yes, you can leave meta variables that have to be unified with some goal that you're trying to meet. But it doesn't support arbitrary higher order unification. So, and I ran into some practical case where I knew that there was some expression with meta variables
Well,
that could directly fit something, but it was not being fit
Yeah.
because of, it was higher order unification.
So that is how I say that the scheme can be expressed in Isabella, but not in Lean, because you say from beginning you somebody run to.
well, in Lean you have free variables, right? Because there is no metalogic, so.
It's a higher order.
Oh, you mean schemes for Grothendieck schemes? Oh, no, not these schematic variables. Oh, sorry. So what, sorry?
That is like the level of design decisions, it's not the small things. But at the kind of day-to-day use level, I already see that there is some advantages to Isabelle. In terms of like the kind of assistance it can provide to you as you're proposing the tools. But you have to balance it with the expressiveness.
Yeah,
of the language.
but if I read some kind of the, how to say, command of the petition, yeah, how he storms it, the program, they say that he use a Lean, and then even the system explaining each step, so that kind of can be the kind of checking and explaining what I did wrong, what I should do next step, is that, or that is the only the use of some extra.
You mean each step in writing the formalization or each step of the proof?
Proof, yes, that's a hit, they can even suggest the how.
Well, I find it, I don't understand how Lean, for example, could do this structured proof, right? Like you wouldn't see where the new auxiliary claim, for example, was introduced. Like here you have just a half.
You can have the same.
You can write half?
Yeah.
Okay, but that's of course like probably like introducing ISAR into Lean wouldn't be too difficult. So that's kind of if they really feel that it's needed, they can do it. So
It's some extra layer to translate it to normal language and so often how is the proof. That means as a mathematician, you want to know that it will a very long group like a shown break to 7 mindset, and each step is a correct, what is can be modified, something like that, right? You cannot say that 200 pages of the petition is correct and
You're talking about Schultz.
yeah, sure. So that means because he had 200 pages group, he ran Lean and say that even can suggest some improvement in this group. So that's that means that that means that I like to, for example, I don't have the 200, but I have the usual sometimes 50 pages of the paper. And group maybe 20 pages, yeah, of some debate.
okay.
So I want to run the checker group assistant. That is correct, my group or not, and where
Yes.
and it's a small trick is possible or not, right? That is the assistant.
But that, in principle, that's what we are probably talking about at the lunch, that you can do that, but it will take a lot of work because you will have to translate your proof in really in you will realize, I think it will be interesting to work, as I said, rewarding, but what you will realize is that you will see that you are doing steps which you were not aware of doing.
Yeah.
Not only that there may be some gaps, but you have a lot of things like that you say, and then somebody asks you why.
Yeah.
Why? And you say, that's obvious. Everybody believes that it's obvious,
Yeah.
but if now the question is, what does it mean, the proof?
Yeah.
Do you really want it down to axioms? No, that's what we tell our students. You never can do that. Now we can see that you can do that, but you don't always want to see it. So it becomes clear that the mathematics is actually very subjective on the level of what you consider as convincing, right? Because proof, after all, is to get convinced, right? And only when we started to understand that we probably don't understand even natural numbers sufficiently, then the logic was created, right? To really, you need a logic whenever there is a disagreement. If there is no disagreement, then I would say, but this is already probably philosophy or something.
So can I make a comment about your question?
Yes, yes.
It's not working. So the story with Schulze involved a team of people who is not Schulze. Right?
Yeah.
Provided the original formal. So the team of people broke down his proof into manageable steps and then it translated each one of them into lean.
Yeah.
And in that process,
Yeah.
they discovered some simplifying insights,
I see.
which then Schulze said, this, this
Okay.
really makes the proof
Yeah.
clearer and
Yeah.
simpler. So those insights were provided by humans,
Yeah.
but they were forced to do so
Yeah.
because they needed to comply to the requirements of the machine,
Yes.
which
Yeah.
that they wanted to set.
Very good, yes, very good. I didn't understand the question, obviously, but I can say, and probably Igor will agree, that this is quite common. This is quite common that you will get a new insight into your proof, which will lead to some simplification or better understanding. That's just actually why we are doing it, kind of. One of the things. That's the joy of it, I would say.
The more powerful the system becomes, the fewer insights you'll get.
It's you control the level of detail. You control the level of detail. Really, my colleagues, if they are in hurry, they want to hurry to their final proof. Sometimes you really run a sledgehammer. A sledgehammer gives you SMT proofs. SMT, satisfiability modulo theory, is currently the most powerful tactics. And it gives you 25 lemmas, saying, using these 25 lemmas by SMT, running time 3 seconds. And that's certainly a point where you shouldn't continue. That's what you are saying. That the more powerful, maybe within the 5 years that I am working on it, it really improved in a sense that when I was starting, I didn't encounter, maybe because I was working on beginnings, but I didn't encounter proofs that I didn't understand. And now I encounter them regularly. And now it comes to the discipline, right? Do I want to leave them there or not? Okay. Will it be accepted in AFP if I leave it there? Or do I do it because I want to put it into AFP to archive, or because I believe I will become famous if I have a lot of entries in AFP, or do I want to understand the proof, right? Comes up to these human questions.
It's important for these proofs to be human readable, or no one going to read it.
Say it again.
Is anybody going to read the proof apart from the computer?
Good question. Myself later. But also, for example, I can use it for teaching. I would use it for teaching.
For teaching the theorem, or for teaching the system?
Teaching the theorem. Teaching the theorem. But this is, well, I have a course on combinatorics on words, so I am always using kind of a bit using Isabelle. But of course, it's usually better to write it on the blackboard than to show it in Isabelle. So you are right. And that's a good question, whether anybody will care. Yeah, that's a good question. So again, I think that the main advantage, apart from the verification, actually, I believe myself that this will improve very quickly. I think that we will reach a point where the verification will be possible even in the, let's say, informal written language, right? Right, that let's assume that blah, 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 right? I think that AI, current AI, already understands what formalized is, right? So I think that we are quite close to the fact, to the situation where the informal papers, as we are writing them now, could be verified immediately. And I even think, probably unlike Igor, that in my lifetime, it will become obligatory to submit verified proofs to journals.
Yeah.
Because the referees are not here
Yeah.
to chase your stupid mistakes, right?
Yeah, sure.
These are valuable people. Their time is precious. They shouldn't be doing
Yeah.
this slavery work to
Yeah.
read bad papers and to hunt down the mistakes, right? That's simply outrageous.
Yeah.
I think that, in 50 years, they will not understand, that the professors at universities were reading stupid papers
Yeah.
within the peer reviews.
Yeah. Yeah.
That simply doesn't make sense, right?
Right.
The human referee should say, is it nice? Is it well written? Is it interesting? And so on, but not whether it's correct.
Yeah.
I just want to maybe attract your attention. So I just shared something from my screen.
Yeah.
This is an example.
Sure.
So this is pertinent to the question whether anybody would read a formal proof. So this
Okay.
is from Glean,
Okay.
which was translated not even by AI, but with some algorithm into simple English. So this is the translation back from a formal proof into human readable proof. But the advantage is that you can, look at any particular stage. You can ask, okay, what is the machine thinking at that point? And you can also say, maybe I don't understand.
Fonts are larger because
Yeah.
Yeah.
Yeah. So, so there's some proof in topology. You look at one sentence, like one can see that, okay, maybe I don't see that. And then you can ask the machine to expand it and so on. So this is not possible in a textbook unless it was specifically designed for that purpose. But in principle, you can go down in this human readable form all the way to whatever the basics are of the logical system that you use. The way that this is.
And what is this system?
This is an experimental
Yes.
kind of like layer on top of me. It's not publicly available, but it's a proof of concept that there's something like this is possible.
Can you see what happens if you keep pressing the plus?
Yeah. So there's even expand all button. So I think
That is a finance.
so it becomes kind of longer, but not even long.
Okay, but it hasn't changed on the list.
They're finite.
Yeah. So I just wanted to highlight that this is a possibility in some systems, which maybe have different design decisions where you store maybe some parts of the proof, where you can then use that to translate it back into something which is human readable.
Yes. And it should be possibly even the other way around. But you will be forced to do the work that we are speaking about, of course.
So sorry.
Can I deliver a fun story?
Yeah.
Okay.
So my first paper was essentially formalized. So and we worked with Barbara Sheik and we focused some problems and do something. I wrote a sort of paper, but it was a paper written out with one something and two something, three follows and one and so. And then he said, well, this is something you cannot publish. So he took it and rewrote it into normal language that was used.
Okay.
It's used in papers.
So you had high expectations from your colleague mathematicians.
Because it's necessary to write it. It's very difficult. But I have three questions. So one is very simple. I forgot what the instruction had means.
It just creates an arbitrary goal. Right, I have a lemma which is a goal, and I can create a new goal. Right.
Asking to do lemma.
Yes, yes, it's the same thing like lemma inside a proof of a lemma. You cannot nest lemmas, so inside the proof have just creates an arbitrary goal, which not necessarily even is related. It's up to you. Like you are just proving facts, and of course, you should be aware that they will disappear after you close the proof.
But can you nest lemmas if you want to go another way?
You cannot nest them in a sense that you open lemma in a proof of another lemma, but of course you are using lemmas. So you prove if I think this is one of the virtues of or should be virtues, or the difference between good formalization and bad formalization is that if you have an ad hoc claim, say, oh, now I have to prove this. So again, bad formalizer, and now it goes to human qualities, that's not related to the system. Bad formalizer will just go on proving it ad hoc inside the proof. But what even the formalization kind of teaches you, but not necessarily, but should teach you, is that you say, okay, but this is actually a general claim. It's a general claim. I have to put it outside as a claim. And that's exactly when you learn something. Because when you write it down, you say, wow, that's useful. And I don't need this assumption. Wow. And then Sledgehammer will surprise you by using it at places where you wouldn't expect it. No, but that's the same thing. No, you cannot. Okay, you can. But you could always, right? Okay, you are right. It needs something. Yes. Yeah. You need to some. But I think that is even kind of bad style now. This having lemmas inside the open proof. No, I mean that's a matter of it's risky. No, kind of. It's a bit risky.
So my colleagues want to the outside.
Let's start with Q. We started with this thing, when the lemmas.
Yeah.
Okay. Yes. From this point of view, yes.
Sometimes
True. Yeah. So it depends. Yeah. Right. You're right.
So this is how big a library was Isabelle, because there is this incentive to prepare a big library for a year. And in this way, they could compete, and the library will be definitely very important thing.
Sure. So the metric, like 100 proofs metric, Isabelle is winning, and now the size of libraries, I don't know, because I wouldn't even recommend to consider sizes, because I have seen, for example, I have refereed even bad papers which were like boasting about the number of lines. But I said, okay, that's the problem. Yeah. You are not, that should be 3 lines actually. Yeah, I know. So yeah, I know. So now, how to measure what is covered? We can go piece by piece, and I cannot really give you. I cannot give you informed like summary. But there are some fields where certainly Lean is ahead, but I don't know. We could say like let's open Jarník and let's see what's in Lean, what's in Isabelle. I would think that, for example, in case of Jarník, everything is in both already.
Yeah, is that analysis?
Differential and integral calculus.
There is such an initiative being
Depending on who is contributing what. Yes. Yes.
Being library needs to have more things about the differential geometry. So it's coming from outside, it's not.
Yes, no, you can do the same. You can submit, there are a lot of that exponential growth. I am a bit worried about the quality. I think that the Isabelle AFP contains a lot of garbage. Which is probably not the case in the lean, because there is a proper refereeing process, which is not so much in Isabelle. But I mean, you probably don't know what's in differential geometry in Isabelle. Yeah, okay. You don't know, and I don't know what's okay. I don't know what's differential geometry in Isabelle either, because I am not interested in differential geometry. But that would be, for example, we could make a case study. Like maybe you will be surprised what's there. Maybe you will tell me that there is nothing. I don't know. I really don't know. Both is possible.
I think the other type, like a Vygotsky, right? Is that the third type?
Homotopy type. It's, I think Koch is based on it. No.
I mean, not based.
Yeah.
Supports it.
It's compatible with
Yes.
There's some development.
Yes, as a different group, yeah. And then, so that completely, because it is a different type of logic, something like that.
Sorry, you use a different type
A different type of logic.
of logic. Yes.
Yeah.
Yes. And I would say even foundations.
Yeah.
Foundational logic, but it's also logic.
So another practical question. So to install Prelium is it seems to be pretty complicated, because you need to install a lot of programs and so on. Is it how is it with Isabelle?
In which sense?
Yeah, PC.
Suppose I want
Oh.
to start
Oh.
Isabelle. How much do I have to download?
This integration, this fact that's this Macarius Wenzel, the main and unique. I think this is probably one of the biggest vulnerabilities of Isabelle, is that it actually depends. The implementation depends on a single guy, right? Very much, too much, right? So if he is hit by a bus, we are in big problem. I think that the community will cope with it, but it will probably take some years or a year. Okay, but it is really, everything is integrated. So you just download it and unpack it, and it opens. But then there can be some frustrations, in a sense that there are sessions, right? So you have to understand like what is loaded and how. You know, this is something, but if you just open it and write Scratch, it opens the Scratch, the theory, and then you import main, then you can more or less start, right, with most things, right? Yes. So for example, if you want to use AFP, you have an you have to download AFP, and you have to know where to register it. So you have to open a root file and write a directory where the AFP is, which is already it is not like automated. You really have to know that you need to add a line with the path to your AFP to this particular root file. That would be probably like the most difficult part, where you can really feel to be lost. But this is already something that you don't have to do if you really just want to try something. If you want just to open it and try to prove something like that, you know, the problem is that it's difficult to find something elementary that you would like to try, which is not yet available, right? So that's a kind of frustrating, right? You would think about like proving that, okay. You would try like that square root of 2 is irrational. And then you would immediately run into a difficulty, because reals is a highly non-trivial thing, and it is not in main, right? Real numbers are not in main already. So you will have to write import main analysis library. And then you will realize that a real number is not a rational number, right? and then you will really get in trouble. But this is not fault of Isabelle, right? That's a matter of fact. And then this is one thing that when you start to think, right? So Q is a different type than R. So even the claim that square root of 2 is not rational, well, it's trivial because it's of a different type, right? So, and then of course you can start to feel frustrated. So, but this is already not the problem is computer. True, exactly. And that will be That's for example, of course, for you will be trivial, but for students, it may be a source of instruction.
So maybe that was a good time to officially
Officially.
end the seminar. So thank Štěpán.
Thank you.